Hello everyone, I am T. Virupakshan hosting today's Geo-Varta session organized by Banaras Hindu University Geophysical Society. This event, Geo-Varta, is comprised of very fine and brief lectures of eminent personalities in the field of earth sciences. And so we have Dr. Sukanta Roy with us as our guest today for delivering his lecture in the very first session of Geo-Varta event. Sir is a brilliant researcher and he is currently working with Ministry of Earth Sciences as project director of Borehole Geophysics Research Laboratory situated in Karad, Maharashtra. Thermal structure of the lithosphere, geothermal energy and geothermics of climate change are his area of expertise. And Sir will be introducing us all to scientific drilling and borehole geophysics, which is very informative topic for all of us whether we belong to earth sciences or not. There are few announcements for participants. The first one is there will be a brief question and answer session right after the presentation is over. Sir will be answering your questions. We will be assisting sir in doing that. You just have to write your questions in the chat box and it will be answered hopefully. Also, there will be two links shared with you via the chat box. The first will take you to the quiz, and the second one will take you to the feedback form. And you have to fill both of them because we will be marking your attendance via it. And the final announcement is for those who are somehow unable to connect with us. They are requested not to worry because we will be uploading this whole session on the our YouTube channel and its link will be shared on both Facebook and Instagram, so it will be easily available to all of you. Okay, so that's it, and without wasting a minute I will request sir to please start the session. Sir, please.
Straight away go to the brief presentation that I have today for you. So, dear students, uh, as Virupakshanand has already mentioned, my name is Sukanta Roy and I work for the Ministry of Earth Sciences, Government of India, in the Borehole Geophysics Research Laboratory, which is located in Karad in Maharashtra. After doing a master's degree in geophysics from Banaras Hindu University, where you are right now located, in 1992, I pursued my doctoral research in geothermal studies thereafter at the National Geophysical Research Institute in Hyderabad and continued there until 2014 before moving to the Ministry of Earth Sciences. At the Ministry of Earth Sciences, I have the privilege of leading a fascinating but a very challenging program of scientific deep drilling investigations to probe uniquely the reservoir triggered earthquakes in the Koyna region in western Maharashtra. The ministry is also developing the BGRL, Borehole Geophysics Research Laboratory, as a dedicated center for carrying out borehole geophysics investigations to study fundamental aspects of earthquake research, of earthquake genesis. So today I will introduce or try to introduce very briefly the topic scientific drilling and borehole geophysics, and I will try to explain with a few slides why borehole geophysics is such an indispensable tool in modern earth science research. So, to start with, I would like all of you to agree with me that geoscientific insights into the deep earth processes is today mostly based on observations made at the surface uh, uh, and through indirect evidences using geophysical investigations or increasingly by modeling. However, several critical Earth science system processes and records of environmental and past climate change, for example, are difficult to observe from the ground surface only. Hence, despite the great advances or the great progress achieved in solid earth science during the past several decades, truly ground truthed knowledge of the dynamics of the Earth's crust is limited. And this is because direct access to the interior of the Earth's crust is only possible through drilling boreholes and making a suite of measurements at deeper levels. Now, as the name implies, to do borehole geophysics, one needs to drill a borehole, either on land or in the ocean or on ice. Boreholes are drilled routinely for exploration and exploitation of groundwater, mineral, hydrocarbon resources, etc., to depths ranging from a few meters to a few kilometers. On the other hand, boreholes drilled for scientific research, which is most commonly known as scientific drilling, are much less common but are extremely important to unravel the hidden information about a wide range of processes, uh, wide range of earth processes associated with, for example, natural resources, climate dynamics, active faulting, uh, hotspot volcanoes, large igneous provinces, impact structures, convergent plate boundaries, subduction zones, geobiosphere, and the early Earth. You can see that no major field of earth science is is I don't know what happened. Uh,
Yes,
yeah,
sir.
can you see?
Yes, sir. We can see that.
Okay, okay. There was some message in between, so I just yeah. So
Okay.
there is no major field of earth science research which is not touched by scientific drilling. Now, the borehole geophysics as a field that includes the entire suite of geological and geophysical investigations that are carried out either in the form of downhole measurements and monitoring or in the form of laboratory studies on core samples and drill cuttings that are retrieved from very deep levels in the Earth's crust. And of course, this includes borehole geophysics includes crosshole studies when you have multiple boreholes. Now, it is very well recognized that drilling followed by borehole measurements has the unique advantage of providing exact, fundamental, and globally significant knowledge of the composition, structure, and processes of the Earth's crust. And therefore, the data that you get from borehole geophysics helps to confirm or reject hypotheses or models that are based on surface geophysics alone. In recent years, boreholes drilled at carefully chosen sites are also used as natural laboratories for carrying out experiments and as observatories for long-term monitoring of ongoing active processes. Now, what are the advantages of borehole geophysics over surface methods? Very clearly, as you go deeper into the earth, for example, inside a borehole, and you record the parameters, you record the physical properties, mechanical properties, etc., you are actually getting a much high resolution data. You are actually sampling centimeter by centimeter or few centimeters at a in one reading, and therefore the resolution that you get is much better than any surface method can give. When you are uh, recording, for example, seismic waves uh, inside a borehole, so by placing the geophones inside a borehole at different levels, you can actually get a very fine scale structure, velocity structure of the region surrounding the borehole. And because you can the the depth control is in your hand, you can actually go at very small intervals, record at very small intervals, and you can hope to obtain the small scale heterogeneities, hope to map the small scale heterogeneities in the rock formation. And as you go deeper and deeper, you are going closer to the sources, for example, earthquakes, for example. And because you are cutting off the overlying rock formations, so you are cutting off a large part of the noise, and therefore your signal to noise ratio also improves. And I shall show you examples of each of these in the work using the data, using the work that we have carried out in the Koyna region in Maharashtra. So here I come back to the main program that I am involved in, and many of my colleagues at DGRL are involved in. This is the scientific deep drilling in the Koyna intraplate zone, Maharashtra. And if you look at the geological map on your left, on the left side, you can see Koyna, which is on the west, in the western part of the Deccan Traps province. You can see the green shaded province on the western part, that is the Deccan Traps, which, as you know, is a result of the 65 million-year-old volcanic episode, volcanism, which happened when India, passed over the reunion hotspot almost 65 million years ago. So today you have the region that is totally covered with basalts, called the Deccan basalts. And the detailed map of the Koyna region, our study region, is shown on the left side, where you can see the Koyna reservoir on the north and the Varna reservoir in the south. These are artificial water reservoirs which were created for hydropower projects. So both of these reservoirs produce electricity, hydropower. But then after the dams, after the reservoirs were impounded, they started the region started showing enhanced seismic activity. So you can see a small region of about 20 kilometers by 30 kilometers area between the two reservoirs is a seismic hotspot today, seismicity hotspot today. And this has been going on since more than 55 years now. This isolated or secluded region has experienced recurrent seismic activity, including a magnitude 6.3 earthquake in 1967, about 20 earthquakes of magnitude greater than 5, about 200 earthquakes of magnitude greater than 4, and several thousand smaller earthquakes. From detailed seismological observations as well as the reservoir water level records. Now you see on the right you have the reservoir water level records. So on the top panel you have the water level fluctuations, water level changes throughout the year, January to December, and this is for different years. The pattern remains the same. You can see a changing pattern of the decrease of water levels in the post monsoon season and up to the summer, and then as the monsoon starts, after that you see increasing water levels in the reservoir. And if you see the frequency of the earthquakes during those few months in this region, you can see that the frequency of earthquakes, the occurrence of earthquakes is very well modulated by the loading and unloading cycle of the reservoir. And this has been seen year after year after year by scientists from AGRI and the Koyna Dam Authority. They have wonderful, very systematic records of the water level data. So this much is well understood. But in spite of uh, so many seismological and other investigations in the last 4 decades, the physics of the earthquakes, the mechanisms of the reservoir triggered earthquakes is still poorly known. And scientists believe that this is poorly known because the measurements are being made at the surface and we do not have any data on the change of physical and mechanical properties associated with the earthquakes from the near field of earthquakes, near field region. That means from the hypocentral region. And in this area, the hypocentral region is between 2 and 10 kilometers. So if you are able to go down to a depth of about 4, 5, 6 kilometers, you will be in the earthquake zone. So from that zone, there is no data directly that people have, scientists have. Therefore, that is a very big information gap. And to address that information gap, the Ministry of Earth Sciences, Government of India, took up this major national program of scientific deep drilling and borehole investigations to directly measure the in situ chemical, physical, and mechanical properties changes that take place uh, before an earthquake, during an earthquake, and after an earthquake. Now, if such a data becomes available, then it will add tremendous value to the present knowledge, and maybe we will be able to know much more about what are the mechanisms of the reservoir triggered earthquakes. And these reservoir triggered earthquakes are very common all over the world. There are more than 100 uh, places in the world where reservoir triggered earthquakes have been reported. Uh, and uh, you can see that in a majority of the cases, the seismicity has died down after a few years. But in Koina region, the seismicity continues even 55 years after the earthquake took place, after the reservoir impoundment took place. So this is a unique site to study the earthquakes, to study the physics. This is almost like a natural laboratory to study earthquakes. Now, while earlier studies utilized the surface observations, a new approach of scientific drilling has been chosen in the Koine area, and this marks a paradigm shift from the practice of setting observatories at the surface station. So, as as is as is in line with the international practice, when you want to go down 5, 6, 7 kilometers, it is not easy. You have to drill 6 kilometers, 7 kilometers borehole, and that is never easy. It's a very challenging thing. And therefore, what is usually done is first a pilot borehole is drilled. So a pilot phase of the experiment, a pilot borehole, is very similar to a pilot vehicle, a pilot car, which moves ahead of the main car or the VIP car, and its purpose is to test whether the route is okay, whether there are any other hindrances, whether the main vehicle can go smoothly. So exactly in a similar way, our pilot borehole was meant to be a test bed before the deep borehole is drilled. So we drilled a 3 kilometer deep pilot borehole. This is also quite deep. We drilled a 3 kilometer pilot borehole, and you can see this in this slide. We show you the drilling rig that was used, and then in the bottom panel, you can see what a big exercise it was. You know, it was a drilling rig and several tens of other heavy machineries, and they had to be mobilized. And in this region, on the left, you can see accommodation for the drilling crew and scientific staff. So we were in this area for about 8 months. It was a fantastic experience, and I'm sure uh, many of you would really love to be part of this experience. Now, this is the deepest borehole in the country that has been drilled in the crystalline basement rocks. And this was this borehole. It went through the entire thickness of the Deccan Traps here and into the granitic basement below. Now, why are we interested in the granitic basement? The reason is that the earthquakes occur below the Deccan Traps, and all the earthquakes are hosted in the granitic basement rocks. And therefore, to study the properties of the granitic basement is of utmost importance. But you can reach the basement and you can sample the basement only if you cross the 1.5 kilometer thick basalt pile. So now there are other very interesting things that you can get from drilling. So this picture is showing how core samples, cylindrical core samples, are recovered from a depth of up to 3 kilometers depth. Work goes on day and night, 24/7 at the drilling site, and you can see here experts are taking out the core, and then our colleagues are marking the core and then scanning them, converting them into digital records. Then other colleagues are studying petrography, like you do in geological studies, when you prepare thin sections and then see them under the microscope. Things like that are being done. Now I'll come to the real borehole geophysics part, where you can see, many of you, I am sure, know what is geophysical well logging. What is done is you lower the different probes, the geophysical probes or geophysical sondes, like electrical resistivity, self potential sonde, the porosity sonde, density sonde, caliper, and so on and so forth. Now, when you sonic velocities, that's a very important one. Now, when you lower these sondes, like this gentleman is doing in the borehole, you go on recording the parameters, the values of the parameters at different depths. Almost continuously, one can record. And on the right hand side, you can see a snapshot of the data, the kind of data that you can get. You can immediately, it strikes. You can see these are the self potential, caliper log, gamma ray log, velocity, shear wave velocity, E wave velocity, Poisson's ratio, neutron porosity, density, resistivity. So all of you, I think, are quite aware with these properties, which are very common properties of rocks. And the kind of resolution that you get in the data as you go down in depth. So this is showing, I think, 1200 to 3 kilometers depth of the granitic basement, and the data is, as you can see, uh, it's very detailed in nature. So detailed that if you look carefully, you can find out different zones where the properties are really anomalous. For example, here you can see below 2100 meters depth and up to 3 kilometers depth, we have we have marked 7 zones, we have shaded 7 zones where the all the properties, all the geophysical properties are highly anomalous. So you can, these must have a reason. But today I'll not go into the reasons. Today my point is to show you what a high resolution data set is and how you can get so much more information about thin, few meters wide uh, depth intervals, uh, 3 kilometers below the surface, which there is no other way of getting this kind of a detail from any surface method. Now, you can do shear wave anisotropy. For example, the left hand side, you can see the shear wave anisotropy plots, different uh, uh, things that you can do with, anybody who has worked in seismics would know the value of these. So you have the slow polarized shear wave and the fast polarized shear wave, and you can extract a lot of information about the anisotropic behavior of the rock formation. Now, if you want to know the temperature, what is the temperature at different depths, how would you get it without actually doing measurements in the borehole? Now, on the right hand side, you can see this is an actual temperature profile in the 3 kilometer deep borehole. And one can have a great detailed information of this, but very uh, very simply, at 3 kilometers depth, we can, from this based on these direct measurements, we can say that the temperature is about 80 degrees Celsius. Now, the value of borehole geophysics, therefore, is really immense and unprecedented information you can get from borehole geophysics. Now, look at these measurements inside the borehole. What are these? These are the image logs. What are these? These are image logs. There are two kinds of imaging tools that are generally used. One is based on acoustic waves, and the other is based on formation microresistivity. And you can see the two kinds of images for different depth zones show such a beautiful detail of the different kinds of fractures, different information about stress. For example, this kind of a fracture, as you see in the middle part, two bands, two parallel bands, these are actually borehole breakouts. And you know, the borehole breakouts give a measure of the ambient stress regime. So you can study the fracture density, the fracture orientations in detail. You can identify the you can get the stress regime, and you can correlate the two. And you can see here on the right hand side, by detailed processing of these geophysical logs, of these image logs, we have been able to find out the orientation of uh, uh, the principal horizontal stress direction, and here on the right hand side with in red color, the strikes of the fractures, the different fractures that have been identified. And these have been marked in 5 different depth zones, depth intervals. Now, these are very detailed data sets, really detailed data sets, and you can get immense information about how the stress orientations, what is the faulting environment in this region, what are the conditions, are the conditions favorable for faulting, are the conditions favorable for failure. Uh, you can do immense lot of things with these data sets. Now, you know seismics. Usually at the surface you have you blast explosives, or you use a hammer and create seismic waves, that elastic waves that go down into the subsurface, and then they return, and you record them using geophones on the surface. But the same geophones, hello, yeah, the same geophones, you can actually plant them inside the borehole at different depths, and record the upgoing as well as the downgoing waves, both. And you can get a very high resolution picture of the subsurface. On the right side, you can see here a borehole observatory. So you have a borehole, and it's a schematic diagram where once we one can see that a an array, a vertical array of seismometers have been installed at different depths inside the in the subsurface, and you can actually record them, do the recording 24/7, and as because you are at such depths, you are cutting off the noise because of the superficial formations, rock formations, and therefore you get very clean records. Very clean records means you can actually detect very small magnitude earthquakes with much greater precision. Not only seismometers, you can actually have other sensors also placed inside a borehole, and this is what is called as a deep borehole observatory. Now, in addition to these, when you drill, you get core samples, and we drilled in an earthquake area. So we were looking for signatures of deformation, brittle deformation, signatures of earthquakes in the rock, in the core samples. So you can see here the top left figure. These are two fractured surfaces showing striations, which are called slicken lines, or slicken lines, striations. So when two rocks move past each other along the direction of the movement, you find these striations happening, and they are very clear signatures that there has been movement. Now you can see small faults along which displacement has occurred in the other figures, the top right and the bottom two figures. If you look carefully, very easily you can see that the felsic bands have been displaced along a fault plane. So these are clear-cut examples of earthquakes or of movement.
Uh, Hello, sir. Okay, we have to wait for a minute. I will be here anytime. Okay, so we have some technical difficulties here. You can fill your quiz in the meantime, and yes, you can go and click on the link and please fill the quiz. We will be uploading the feedback form as well.
Hello, sir. Are you there? Am I audible?
Yes, Vishal, you are audible, but I think sir has a connection issue.
Yes,
Uh,
but he can change the slide.
yeah, but what's happening here?
Of solid geophysics.
Yes, sir is back.
Sir,
For example,
sir,
pardon?
sir,
Yeah,
we have
yeah.
missed a little bit of your audio in between.
From where?
Sir, I think the last slide. We have missed the last slide, sir.
Okay, okay. Now can you hear?
Yes, sir, we can hear you.
Now can you hear? Okay. So I will repeat it. In summary, what I wanted to say is that scientific drilling, you have already seen from this very brief presentation about only one example from an earthquake investigation, that what is the utility, what is the utility of scientific drilling and borehole geophysics. That scientific drilling is really an indispensable tool of modern earth science research. The scope of scientific drilling and borehole geophysics are immense and are poised to grow rapidly, as both industry and the academia realize its potential to provide low cost, provide cost effective and direct information on the processes operating at depth. You may have also realized that immense utility of borehole geophysics exists in almost every field of geophysical exploration and research. You are well aware already of the opportunities that exist in the hydrocarbon industry, for example, in petrophysics, reservoir geophysics, geomechanics, etc., and in the geophysical well logging and log interpretation in mineral and groundwater exploration and exploitation industry. However, I would like to add here that scientifically very exciting and new and high-end research opportunities have opened up in frontier areas of solid earth geophysics. For example, in when you go for understanding the complex physics of tectonic faulting and earthquakes, for example, you have very in US and in many other places, you have this injection induced seismicity that is associated with the fracking for shale gas and geothermal energy and things like that. You have engineered geothermal systems where you drill a borehole, you send water or fluids through that borehole, and nearby you create another borehole from where you take out the hot fluids and use that as a geothermal resource. But What you need to do is at that depth, in a very high temperature environment, you have to create a heat exchanger, which you can do by hydrofracking. And therefore, this is not possible at all without very careful borehole geophysics investigation. Now, another example, for example, you know the magmatic heat source, so magma. Magma is a very high, very rich source of geothermal energy. But then, really, it is not, today, no technology exists to exploit this kind of energy. Now, uh, if you want to do high-end research, you know, small fraction of this magmatic heat source can serve to cater to the energy requirements of the whole world. But then, how to exploit it? How to mine that heat resource? So that requires very careful, very comprehensive, very elaborate investigations, which can be only done through borehole geophysics. I would like to just add here also that because you all are students and you must be either starting your course or you must be completing and then going for the industry or for research elsewhere in the world. So I would like to also share with you that top research institutions and universities in the world are now engaged in a very big way to address such complex problems using novel experimental and computational techniques. Therefore, students, it is a very opportune time, according to me. It's a very opportune time to take up geophysics as advanced research in borehole geophysics. I will conclude my talk here, and but before I say bye, I must say that I remain thankful to the Banaras Hindu University student chapter of the Society of Exploration Geophysicists for this opportunity to return, although virtually, to a place that is very close to my heart and share my thoughts with budding researchers in geophysics. And I must also really compliment from the bottom of my heart the Geo-Aakarshan team, the advisor of the Geo-Aakarshan team, and the student members who have done a fantastic job. They have with our geophysical fraternity. So all the best. Thank you very much.
Okay, sir. Thank you very much. Sir, shall we start the question and answer session?
Yes, I'll try to uh, I'll try to answer
Uh,
at least some of the questions.
yes, sir. Okay, sir. Okay, participants, you are requested to please write your questions, if any, in the chat box. Sir, I have a few questions here. Is FMI
Yeah,
the only log to detect fracture by SAF?
by
Sir, the participant's
by
name is SAF. So,
okay. Now FMI is actually a Schlumberger term, which is the full form is formation micro resistivity measure. It's a basically imaging tool which is dependent on formation resistivity. Yes, that is a very good tool. But then you have also another tool which works on acoustics. So it's the in Schlumberger terms it's called the UDI, but it's basically a borehole televiewer which uses acoustic waves to image the formation.
okay, sir. And I think SAF got his answer. Sir, the next question is how can we use gamma log in drilling?
Gamma log is natural gamma log is the most common log that is used uh, in geophysical well logging after the drilling is over. There are multiple uses. It's actually used as a lithology as a proxy for lithology, as a as a proxy, as in depth matching, you know, there is always a difference between the driller's depth and the logger's depth. So the logging depth and the drilling people, they give their depth. These two are these two often don't match exactly, and therefore the gamma log is used for correlating and depth matching. So to get at a at a consensus depth. And yeah, there are other advantages of the gamma, but these two are very commonly used, and therefore with most of the tools during well logging, you definitely want to have a gamma tool associated with each logging run.
Okay, sir. What is the benefit of borehole drilling provide than normal logging? Ankur is asking.
I did not I did not get the question really, because normal logging, by normal logging, what do you mean?
Uh, yes, sir. Uh,
See, borehole drilling is a drilling process. Logging is a logging. Logging means making measurements at different depths and recording the data. That is called logging.
okay, sir. And sir, there is a question from Akash. Can it be said that reservoir-induced seismicity is analogous to hydraulic fracturing?
No, no. Reservoir hydraulic fracturing. In hydraulic fracturing, what you do is, as the name implies, you you pump in water at a high pressure inside the formation, and with that water pressure you try to create fractures, you try to open up fractures. Okay, so that's hydraulic fracturing. And hydraulic fracturing, you can get the directions of stress, you can get the stress magnitude, stress orientation of that region. Reservoir induced seismicity, on the other hand, is completely different. Uh, Reservoir-induced seismicity means the seismic activity that is induced or that is caused by the action of a reservoir. So when you load a reservoir, what happens is you have the reservoir load acting in that region, right? So that load is there. So you have the elastic stresses due to the load, and then you may have pore pressure increase due to the compaction due to the load, or you can have a combination of both. You could have a pore pressure diffusion, which so these are the different triggering phenomena which can actually trigger an earthquake uh, when you have an existing subsurface fault. Okay.
Yes, sir. Okay, sir. And this is a question from Ayush. While logging, we have drilling mud logged out. Why don't we analyze that mud instead of using a logging tool?
Yes, it's a very good question. Actually, the drilling mud is also logged in in certain cases. That is done. Uh, uh, the drilling mud. Uh, for example, you can actually sample that drilling mud that comes out after drilling for analyzing the formation gases like carbon dioxide, methane, helium, and these gases in the formation. So these gases have different utility values. For example, in a hydrocarbon field, methane may be useful. For identifying fault fracture zones, helium may be useful. Okay, so yes, that is used in certain cases,
Okay, okay,
but
sir.
it is not a replacement of a it is not a replacement of a well log. It is not a replacement of a well log.
Okay, sir. I think Ayush got his answer. And the last question we will take will be from Shubham Mohanty, who is asking which log is most used in mining work. I think you have answered it, but
Yes, I would like to again stress, and you know that, most
yeah.
of you know that one log, one particular logging tool is never adequate for any exploration program, whether it is mining exploration or any exploration. You need a combination of logs. Okay, so you just cannot depend on one log only, and it is never done. So that's why we say always a suite of logs, depending on the purpose. So for example, in mining industry, you may use the gamma log, the spectral gamma log. It depends on what are you looking for. If you're looking for radioactive minerals, you should definitely go for a spectral gamma log. Then you should go for regular mining logging. You should go for the other logs, as density log, neutron porosity, self potential. Self potential is a very important log. Electrical resistivity log. So I think these logs you should go for. Never depend on one log.
Okay, sir. So, yes, sir, there aren't any questions anymore. So, okay, sir. Thank you very much for giving us the opportunity to have you with us. And the lecture was really, really informative. And we can see that from the participation. Thank you, sir.
Thank you very much. It was a pleasure talking to you and sharing our work with all of you students. Bye bye.
Bye, sir.
Bye.